Welcome to this presentation entitled Enhanced Dune Building Processes with Nature-Based Nourishment Design. My name is Caroline Hallin, and I currently share my time as a postdoctoral researcher between TU Delft in the Netherlands and Lund University in Sweden. And before kicking off this presentation, I would like to acknowledge my co-authors, Sia de Vries and Christa van Eysendorn at TU Delft. This study is part of the Dune Force project, which is funded by NWO. The problem at hand is that dune growth in nourishment projects sometimes turn out lower than what could be expected. There are some examples from the Netherlands, for example, the Sandmotor and the Hondsbosje dunes, where the dune growth does not match expectations. And we learned from the Sandmotor that building a huge beach out of nourished sand does not necessarily lead to large aeolian transport and dune buildup. This is due to supply limiting processes. There is simply not enough sediment available that can be picked up by the wind due to, for example, armour layer development and surface moisture. And the supply limiting processes depend on design conditions, for example, the grain size sorting, and beach morphology. The grain size may be too coarse for the local wind climate, and armour layers can develop that cannot be broken by hydraulic mixing if the beach is too high, etc. And these are complex relationships that are difficult to predict. So in this study, we give it a try. We investigate how process-based models can be used as a design tool to promote dune growth in nourishment projects. The process-based model Aeolis has the capability to simulate aeolian sediment transport and sediment availability in the bed. In Aeolis, multi-fraction aeolian sediment transport is implemented through an advection scheme with grain size selective pickup and deposition. The saturated sediment concentration is based on Bagnall's equilibrium transport equation. And the transport is maximized by the available sediment in the surface layer of the bed. The net entrainment is computed for a range of grain size fractions and adjusted with a weighing factor based on the grain size distribution in the bed and in the air. I will not go into details on the Aeolis model, but I will briefly discuss some supply limiting factors in the model. So first, let's take a look at Bagnall's equation here to the left. It describes the equilibrium aeolian transport rate, and I think most of you are familiar with it. In Aeolis, supply limiting factors are implemented through modifying the critical shear velocity, which is circled here in red. And the critical shear velocity, the equation to your right, depends among other parameters on the grain size. So fine sediments will be eroded more easily than coarse sediments. And the coarse material that is left behind may shelter the fine material in the bed from being eroded. In this way, the bed roughness will also increase the critical shear velocity. And further, surface moisture causes intergranular cohesion and adhesion of water particles to the sand grains that also increase the critical shear velocity. So these three are examples of supply limiting factors that are simulated in Aeolis. And for this application, the surface moisture module has been extended compared to previous versions. The new surface moisture module in Aeolis computes the surface moisture within a thin layer, about 2 millimeters thick, and it accounts for the processes displayed in this schematic picture. I will explain them one by one. First, the groundwater table. The groundwater table is simulated with the nonlinear Boussinesq equation, extended with wave run-up infiltration as proposed by Nielsen et al. And it has a moving shoreline boundary, which is limited by wave setup or the seepage phase, if a seepage phase is present. The surface moisture due to capillary transport from the groundwater table is computed with the soil-water retention relationship, including the effect of hysteresis. And the transition between drying and wetting conditions are described by scanning curves following Moalem. Evaporation and condensation are implemented through the Penman equation, which takes into account air temperature, global radiation, atmospheric pressure, and relative humidity. So those are meteorological parameters that are needed as input to this model. And finally, the precipitation and run-up. In this surface moisture module, infiltration is not simulated explicitly. Instead, we assume that run-up and precipitation drains until soil moisture reaches field capacity. And this takes place in the consecutive time step of the run-up or precipitation event. Here are a couple of animations showing the variation of the groundwater table to the left and the surface moisture to the right. We see how the surface moisture content is varying with the groundwater table, and there is also a couple of rainfall events wetting the entire beach. And if you take a look at the beach profile to the left, that is the yellow line in that figure, that is the beach profile that we are using in the demonstration cases that I will now present. The simulation period is 1 year, and the data on forcing conditions and the soil hydraulic parameters are taken from the Holland coast, which is indicated with the red line in the map to the left. And from the Holland coast, we have also selected average morphological parameters. That is a beach slope of 1/20 and a dune toe height of about 3 meters above mean sea level. And we run the model with different grain size distributions. We use uniform grain size and typical distributions of native and nourished sand. So I will start by presenting the most simple case. In the first simulation, we ran 3 cases of uniform grain sizes, 0.2, 0.3, and 0.4 millimeters. And here we look at the accumulated volumetric transport of sand into the dunes during 1 year. And in the case of uniform grain size, armour layers cannot form, and we have turned off the moisture process in these simulations. We see that the aeolian transport is event-based. There are some significant jumps in the curves. And we also see that the transport rates are higher for the finer grain size. So the red line with the sediment grain size of 0.2 millimeter has the highest transport rates. But these rates are very large compared to the observed upper limit on the Holland coast. And this shows that to obtain a realistic result of the aeolian transport simulations, it is important to include also supply limiting factors. In the next simulation, we use both a natural or native sand and a nourished sand. And here we can see the effect of armour layer development. First, look at the solid lines. The 2 types of sand have similar D50s, but the nourished sand in red has a higher content of coarse elements. And that is causing supply limitation due to bed roughness, and thus a lower transport rate than the native sand in blue. The dashed lines show the importance of hydraulic mixing. In those simulations, we turned off the hydraulic mixing, and we see that the transport of the nourished sand shows a significant decrease from about 20 to 5 cubic meter per year. And this example illustrates the effect of having, for example, a too high berm, where the armour layers cannot be broken up by hydraulic mixing, because the run-up simply doesn't reach the armour layers. And if we look at absolute numbers here, we have transport rates in the order of 20 to 25 cubic meter per meter. This result is now much closer to the observed accumulation rates in field, but they are still a bit high for this range of grain sizes. So let's see what happens if we also include the process of moisture. Here again, the blue line represents the native sand and the red is the nourished sand. And the solid lines indicate the transport when surface moisture processes are included, and in the dashed lines, surface moisture processes are not included. And we can see that the transport rate for the native sand is, as could be expected, slightly lower when moisture is considered. But for the nourished sand, the transport decreases significantly. The explaining mechanism is that the intertidal area is the most important source of sediment supply when armour layers have developed on the upper beach. It is in the intertidal area that most of the hydraulic mixing occurs, and this is also where we get the highest percentage of moisture content and thus the largest reduction of transport. So, to conclude, the results of this study indicate that the process-based aeolian transport model can be used to explore complex relationships of supply-limiting factors. But remember, aeolian transport is only one design parameter among others, and our simulation showed that finer sediments give larger dune growth, but they are also more easily eroded by hydraulic transport processes, so there needs to be a balance. And for simulations of timescales that are relevant from a coastal management perspective, it is necessary to also include marine sediment transport processes. And in the Dune Force project, we are currently working on the coupling of aeolian and marine sediment transport models. So I hope that we can present some nice results from that study when we meet in the next conference in Sydney, hopefully. So that was all. Thank you very much for listening, and I'm happy to take any questions.